Hello there, and welcome to this collection of notebooks and tutorials on multi-rate signal processing. This is a course offered by Professor Schuller at the University of Technology. I am Renato, the instructor for these online materials, and on this notebook we'll talk about optimization of filter banks. So let's get started. Our goal is to obtain a filter bank from our structure or our product. It's the folding matrix times the delay matrix and so on, which has good subband filters. For example, good or sufficient stop band attenuation and not much passband attenuation. An example could be a desired stop band attenuation of -6 dB and a passband attenuation of less than -3 dB. So what's the problem to solve? The coefficients which determine the frequency response are the coefficients in our cascade or our product and are the coefficients in our matrices. They result in the frequency response in a nonlinear way, hence the usual filter design approach, they don't work here. So previous approach like the Remez exchange algorithm, for example. So those traditional filter design methods or algorithms can also be seen as an optimization algorithms for more or less linear problems, or maybe quadratic if we take the mean squared error. We know that we can read out the result in analysis baseband prototype impulse response HA of n, for instance, by computing the sparse folding matrix of the product given here, without the transform matrix T. And then if we compare it to equation 1 from lesson 14, it was this matrix shown here with this diamond shape. And then in this way we can obtain a HA of n and hence its frequency response from our matrix coefficients. So we can do the same for the synthesis side, or if we restrict that our matrices to have the determinant equals to -1, and then in this case the synthesis baseband impulse response is the same as for the analysis. Another possibility to obtain the analysis baseband impulse response is to compute the polyphase matrix PA of Z, and the first column contains the polyphase elements of the first subband filter in reverse order, and this can be used to read out its impulse response H0 of n, and then to obtain the HA of n we simply divide H0 of n by the modulation function for the first subband for k equals to 0. So what's our approach? Since we now have this nonlinear dependency of our baseband impulse response from the matrix coefficients, we need to use some more powerful optimization algorithms which are made for just mostly convex error functions. First we'll define an error function, and then we will use an optimization algorithm to minimize this error function. This error function can be the sum of the magnitudes or the sum of the squares of the magnitudes of the differences between our obtained frequency response, given our unknown variables at some point, and our desired frequency response. To give the stop band attenuation and the pass band ripples different weights, we can also assign weights to the different frequency regions for our error function. So our starting point is a vector of all our unknowns of our matrices. So this vector is called x. And now we define a function in which computes the baseband impulse response out of these unknowns by multiplying our matrices to obtain our final folding matrix or the polyphase matrix, and then we read out the baseband impulse response. So this then yields to baseband prototype for our coefficient set x, which we will call hx of n, and this is now used to compute a weighted frequency response at k frequency points with weights wy for each frequency point. So this is given here, and you can see more at this paper from the IEEE transactions of signal processing, new framework for modulated perfect reconstruction filter banks by Professor Schuller and Smith. For instance, we can use FracC to compute HI. By default, it computes 412 equally spaced frequency points, and then we multiply this h of I with the weights w of I. And we choose as many frequency points as necessary to sufficiently cover our frequency response. Usually it should be several times the length of our filter to avoid sampling the frequency response accidentally near its zeros. So the more important frequency points in terms of attenuation, they will get higher weights. The same can be also done for the synthesis, but remember that this is only necessary if we don't have the determinant equals to -1, because when we have the determinant equals to -1, we obtain identical prototype impulse responses for both the analysis and the synthesis, so we only need to optimize the analysis. Well, we can see this, we've seen this on lectures 13 and lectures 14. We also need to have a vector containing the weighted desired frequency response, which would be 1 for the passband multiplied by the corresponding weights, and zeros in the stopband. And we will call this D for desired. So when we have all of this, our error function of our vector of unknown x will be, for example, this equation here. And we have a row times column vector. Now we just need to minimize this function f of x with respect to our vector of unknowns x. And this leads us to optimization problem in general. The goal of optimization is to find the vector x which minimizes the error function f of x. We know that in a minimum the function's derivative is equal to 0. So the derivative of this function with respect to x is when it's equal to 0, we have a minimum. So an approach to iteratively find the zero of a function is called the Newton's method. Take, for example, some function f of x, where x is not a vector, but just a number, and then we can find its zero as described here in this picture. We start at some starting point, and then we calculate some tangent, then we get next point, and then we calculate tangent, and so on and so forth in this iteration. So xk plus 1 is equal to xk minus f xk divided by the derivative of 4k equals to 0, 1, 2, and so on. Observe that sometimes we need to compute the derivative numerically by evaluation of the function a few times in the neighborhood. So for example, we will compute delta f divided by delta x for a small delta x, and there are more involved methods for it. So now we want to find the zero not for f of x, but for the derivative. So hence we simply replace f of x by f prime x, and we obtain this iteration here. So now we have xk plus 1 is equal to xk minus the first derivative divided by the second derivative. So to obtain a minimum, not a maximum, we need the condition that the second derivative is greater than 0. So let's take a look into an example for finding a zero of a function using what we just seen. So in this example, we will compute the square root of 2 numerically by finding the zero of the function f of x is equal to x squared minus 2. We know that the solution of this function is square root of 2. So now we apply the Newton's method to find the solution numerically. So we take for the first derivative, that's going to be 2 times x, and then we calculate this Newton's iteration from this formula, and then we will get what we want. So in Python we will start with a value of 1, for example. So x is equal to 1 is our starting point, and then we will do this iteration. So this is what we have here, x minus x squared minus 2 divided by 2x. And we see that the true value for the square root of 2 is given here, and only 3 iterations we obtain this value with 6-digit accuracy. Another example is, for example, to find the minimum of the cosine of x. We know the minimum is of the cosine of x is at x is equal to pi. So this is also a way to numerically determine pi. We have that f of x is the cosine, so the first derivative is minus sine, and the second derivative is minus cosine. So now our Newton update, so x new is equals to x old minus the first derivative divided by the second derivative, and then we'll have that the sine divided by the cosine. And we can also do this in Python. Well, this time our starting point will be equal to 3, and then we will run this iteration where x new equals to x old minus the sine divided by the cosine, and we see that this iteration indeed converges to pi, and it computes pi is equal to 3.14 with an accuracy of 10 digits after only 2 iterations. So we can see this if we start, our starting point is equals to 3, and then we will do the Newton update, and we have 3.14. So if we start x equals to 1, our starting point, it will converge to 0, which is a maximum of our function. So this is what we had before. So it converges to 0 with some rounding errors, of course. We have here 3 iterations, and we see that it converges to 0, which is a maximum of our function, and which also has the first derivative as 0. So this is a very important point, because this shows that we still need to check the second derivative to see if it is a minimum or a maximum. If we start with x is 100, and then we will get that it converges to 32 times pi, which is a minimum, but perhaps is not the expected minimum. So this shows that the starting point is very important for the Newton's method. It's very important usually for optimization algorithms. For a multidimensional function, where the argument is x is a vector, not a number, the first derivative is a vector called gradient, and it has the symbol nabla. And now we need the derivative with respect to each element of the argument vector x. So this is our function. This is not a number now, this is a vector. So the gradient of this function is given by this vector here, and we have the derivative of the function with respect to x1, x2, and so on and so forth until we reach xn, where n is the number of unknowns in our vector x. For the second derivative, we need to take each element of the gradient vector and again take the derivative to each element of the argument vector. Hence, we obtain a matrix, and this is called a Hesse matrix, and it's a matrix of second derivatives given here. Observe that this Hesse matrix is symmetric for reasonable functions that we consider like continuous functions, and using these definitions we can generalize our Newton algorithm to the multidimensional case. So the one-dimensional case was given by this iteration here, but now it will turn into the multidimensional iteration. So this is not a number now, we're dealing with vectors. So we see here, this is the inverse of the Hesse matrix, and here's the gradient of the function, and these are our vectors. For a minimum, this Hesse matrix must be positive, definite, so all eigenvalues are positive. The problem here is that for the Hesse matrix we need to compute n squared second derivatives, which can be computational too complex, and then we need to invert this matrix. So what we can do is to make a simplifying assumption that the Hesse matrix can be written as a diagonal matrix with constant values on the diagonal. Observe that this is mostly a very, very crude approximation, but since we have an iteration with many small updates, it can still work. So now we will assume that this Hesse matrix is 1 divided by alpha times the identity, And the best value of alpha depends on how good it approximates the Hesse matrix. Hence, now our iteration will go from this, with this inverse of the Hesse matrix, the gradient, and it will turn with this crude approximation to this one here. So we have x of x new is equal to x old minus alpha times the gradient of the function. And you see now those are vectors. And this is much simpler to compute than this one here. And this is also called the steepest descent, because the gradient tells us the direction of the steepest descent, or is also called the gradient descent. This is a very important method used in many machine learning applications and on deep learning and so on. We see that the update of x consists only of the gradient scaled by a factor alpha. So in each step, we reduce the value of f of x by moving x in the direction of the gradient. If we make alpha larger, we obtain larger update steps and hence quicker convergence to a minimum, but it may oscillate around the minimum. For smaller alpha, the steps become smaller, but will converge more precisely to the minimum. Because of the update direction along the gradient, this method is also called gradient descent. Let's take a look at an example to see in practice what we've just discussed. So in this example, we will find the two-dimensional minimum of this function given here. So it's a function of x1 and x2, and it's the cosine of x1 minus the sine of x2. So the gradient of this function is minus sine of x1 minus cosine of x2. In Python, we will have the same approach. So we will have a starting point, and then we also set an alpha, and we have this iteration. So in this case, alpha is equals to 1, and the starting point will be 2 and 2. And what we have here, after some 3 iterations, is a value of pi, and a value of pi divided by 2. So we see that the minimum is obtained for x1 as 3.14, 15, 9, and so on. So this is the exact value of pi, and this is what we got. And x2 is the exact value is given here, and we obtain this. So we observe that we needed 3 iterations to obtain 9-digit accuracy in this 2-dimensional case. For the 1-dimensional case with the Newton iteration, we needed only 2 iterations to get the same accuracy. So now we can move on to an example for the optimization of an MDCT, a filter bank, using all the theory and some examples that we see during this tutorial. So we will define a function we'll call optimum_fun MDCT that will contain an optimization of the baseband prototype with the determinant equals to -1 for a given number of subbands. So maybe, for example, we'll see for n equals to 4 and n equals to 16. So we start importing our libraries. We are going to use NumPy, we're going to use SciPy, optimize SciPy signal, and we are going to use matplotlib pyplot to plot. We will use again this function that we used many times before. So this is a function that multiplies 2 polynomial matrices. We've seen this in previous tutorials. We have our delay matrix, we've also seen in previous tutorials. Then we have this function to produce the folding matrix F, and we also seen this before. And then we will have a function that extracts the analysis baseband impulse response from this folding matrix of a cosine modulated filter bank, and we'll put all of this together. So We'll start with n equals to 4, so this is the number of subends, and then we will have our starting point is a vector of random numbers. So we will generate these values for this vector randomly. So then we calculate our folding matrix Fa using this vector with the initialized values generated randomly. Then we also compute here our delay matrix. We will get our Fa of c by multiplying these two. Then we will have our impulse response by reading out this, extracting these coefficients from our Fa folding matrix. So this is what we are doing here. So then we are plotting our initial impulse response from this vector that was randomly initialized. So this will be our starting point, and then we will take the initial frequency response from this starting vector x. We will plot it. Then we will plot our desired frequency response. In this case, our desired frequency response is calculated here. So we will have ones for the pass band and zeros for the stop band, and we will also have a transition band. And then we will plot the desired frequency response. We will also plot the weights, because as we've seen before, we need to give weights to have our error function, and later on we will define our error function. So our error function, for example, can be the difference between the desired frequency response and the frequency response that we have, and we'll multiply with the weights, and then we'll sum these values, but we will see this later. So first, here is the initial impulse response from this starting vector x0, so these are random numbers. Then we get the response, so it looks like this. This is the desired frequency response. So what we will do is that we will change the values and do this optimization so that this tries to approximate this. And here we have our weights. So our weights, we give high values to the stop band and 0 to the pass band, and we have here a transition band. So this is the principle. So now we are defining our optimum func MDCT. So this will compute the error function for the filter bank optimization for coefficients x, a 1D array with n subbands. So we are doing the same what we are doing here, but in the end here we have our error. It will be the sum of the absolute value of the frequency response minus the desired frequency response times the weights. So this is our error. So up until here we are doing the same that we done here, and now we calculate the error, and this function will return the error. So now we will use this function. So if we want to see, for example, n equals to 4, so we will initialize our starting vector, and this will print the starting error, so it will calculate this error for this initial value. Then we want to find the x minimum, so we are calling here this optimize minimize, and it will minimize this error. So we are passing this function here with this starting optimization vector here, and the argument is the number of subbands we are passing here, and then we will print this optimized coefficients. We can also save them, and this will be the error after the optimization. So after we find this minimum, we calculate the error, and this is we'll see now from this vector, which is the minimum with the minimum error, is the optimized coefficients. We do again the same procedure, so we calculate our folding matrix, we multiply the folding matrix with the delay matrix, and we read out the impulse response from the folding matrix, and we will plot the resulting impulse response and the resulting frequency response. So when we run the cell, I also want to see how much time it will take, so I'm including this Python Jupyter Notebook magic for this cell, and we see we start. This would be our random initialized vector, our starting point, and it has a starting error given here. Then this is some information given by our SciPy signal optimize, SciPy optimize minimize, and we have it here. So these are the optimized coefficients. So after we run here to be here, this x min. The error after optimization is this one. So you can see there is a difference here. And then with these optimized coefficients, we will get our impulse response, and now we will plot the impulse response. So it went from something like this to this, and something like a initial frequency response like this to this frequency response here. And it took 20 seconds to calculate this optimization. So it starts with random coefficients. We'll print the resulting error value. Then it optimizes the coefficients using the SciPy optimize minimize. Then after it's finishing this optimization, it will print out the resulting error value like we've seen before. And then we have here the resulting baseband prototype and its magnitude frequency response, what we see here. And we observe that this resulting baseband impulse response is very similar to the sine window, but not exactly the same, because it is more optimal in our optimization function sense. So this was for n equals to 4. We can also see n equals to 8, so we can run our cells. Let's do this. So it's calculating. This was the starting error. So we see it takes more time than with 4 subbands. Now here's the result, and it took almost 1 minute, and it looks like this. And here is our magnitude frequency response. And also for 16 subbands, it took 1 minute and almost 2 minutes, and we have our optimized baseband impulse response for our optimized MDCT filter bank. Here the impulse response, and here the magnitude of the frequency response in dB. So that's it for today. This was our tutorial on the optimization for MDCT filter bank, and I see you on our next tutorial.